Hello and welcome to this next lecture on machine learning. In this session we will discuss support vector classification. You might recall that we had invoked the support vector formulation for regression. We will do the same for classification today while introducing the general representer theorem and reproducing kernel Hilbert spaces. So recall our discussion on perceptron, which does not necessarily find the best separating hyperplane, it finds any separating hyperplane. So pictorially what this meant was, if you had some negative points and some positive points here, the separating hyperplane could have landed up being something like this, invariably passing through one of the points. Now this bare separation of the positive and negative points isn't very useful for generalization. What if you get a positive point which lies here? Well, it will be classified as negative. So what you really want is a separating surface to have good margin between the points, and this is what you would like. In fact, we are fine having the separating surface in no man's land. So what we want is a separating surface to provide enough breathing space, and by breathing space we mean the space in green. We have already seen how the support vector formulation for regression helps achieve the same. We will see the same for classification. Since we have most of our machinery in place, we will be able to develop this fairly quickly. Let us start with a separable case. In this case we do not have the problem of entertaining any point within the margin, so we can go ahead and say that the function applied to any point, the linear function fx, should be greater than +1 for the positive points and less than -1 for the negative points. +1 and -1 are somewhat arbitrary. You could have rescaled the w's, the b's and this margin. So what you would like to do is, subject to these constraints, you would like to maximize margin. Now what is a margin? We will see that in the subsequent slides. So what about the non-separable case? In this setting we will need to introduce slackness parameter for every example, pretty much like in the regression case. However, because we expect the positive points to all lie on one side and the negative points to lie on the other side, we will have only one slackness for every point. So what will this amount to? We will say that for each I that is positive with yi equals +1, we will need fxi to be greater than or equal to 1, but now this point could lie inside the margin, or it could actually even spill over to the other side of the separating hyperplane. So fxi should be greater than or equal to 1 minus xi. Likewise, if yi were -1, you would like fxi to be less than or equal to -1, but again the point could spill over to the other side or even lie within the margin, so -1 plus xi. Now we could actually bring these two inequalities into one form by just multiplying them by yi. We note that the right hand sides of these two inequalities are exactly opposite signs, whereas the left hand sides are exactly the same. So therefore if you multiply the left hand side by yi, with the swapping of the signs of yi, the inequalities will change. So the first inequality will remain greater than or equal to, the second one will also become greater than or equal to, it will change. So therefore you get yi times W transpose phi xi plus b greater than or equal to 1 minus xi. Now back to the margin. What is the margin? Well, let's imagine 2 points x plus and x minus that lie on the supporting hyperplanes. This is a separating hyperplane, this is the margin hyperplane on the positive side, this is the margin hyperplane on the negative side. So this is a point x minus on this margin hyperplane on the negative side, and here is x plus. Now what we would like is to measure the distance between these two margin hyperplanes. We do that by projecting this vector phi x plus minus phi x minus on the vector that is orthogonal to the separating hyperplane. The equation of the separating hyperplane was W transpose phi x plus b equals 0, that for the margin hyperplane on the negative side is W transpose phi x plus b equals minus 1, and the other hyperplane is W transpose phi x plus b equals plus 1. Also, the actual representation of the points is in the space of attributes phi. We are not interested in the magnitude of W, so we consider the unit vector that is normal to the separating hyperplane, and that has direction W divided by the norm of W. So this is what we are looking at, the projection of phi x plus minus phi x minus on W by norm W. Now what exactly is the value of this expression? First of all, we note that W transpose phi x plus b equals plus 1 and W transpose phi x minus plus b equals minus 1. So we could actually put together these two equations, the one in blue and the one in red, and simplify this dot product. Now if you were to add 1 and 2, you would find that you are able to simplify the margin expression. You get W transpose phi x plus minus phi x minus, this dot product equals 2, the b actually gets cancelled out, and the margin expression thus simplifies 2 divided by norm W. So we want to maximize 2 divided by norm W. You could also get norm W in the numerator and talk of minimizing 1/2 norm W. One could also look at the square of this expression for the convenience of differentiation and so on, and equivalently minimize 1/2 norm W square. Of course we are now talking of the L2 norm of W. So let us formulate the optimization problem. You need to find W star and B star that maximize the margin 2 by norm W, or as I pointed out earlier, you might want to minimize 1/2 norm W square. You want to do that subject to the constraints that modulo the slackness parameters xi, the positive points lie as far as possible beyond the positive margin hyperplane and the negative points lie beyond the negative margin hyperplane. Now there is a problem with this restricted formulation. Note that as xi tends to infinity, that is 1 minus xi tends to minus infinity, you can very easily satisfy these inequalities even with W tending to 0 and B tending to 0. So inequalities get easily satisfied even with W tending to 0 and V tending to 0. And note that as w tends to 0, which means every component of w tends to 0, 2 upon norm w tends to infinity. So this basically maximizes the margin 2 upon norm w. This isn't especially what we were expecting, because this will give us a very trivial solution. Have we missed out on something? Well, it's obvious that xi I should have some more constraint. So what are the modifications one could make to this formulation? Well, here are some alternatives. You could add a penalty, let us say minus of summation xi I to the objective. So what we mean by this is that we want to maximize the negative of the summation of the slacks or minimize the summation of the slacks. We would like each of them to go to 0. So this encourages small xis. One could also look at adding the sum of the squares of the xi's to the objective. In such a case, one can drop the positivity constraint on the xi's. Recall that we have discussed this variant in the support vector regression setting. One could also add a constraint to the objective such as xi I less than equal to theta for all I. While all these are possible, we will consider the first modification, and in fact we will add a trade-off C between the margin and the error. So we will minimize the summation of the xi i's. This amounts to minimizing the error. Of course, we want to minimize the error while maximizing the margin. Now, to solve these two problems together, the minimization and maximization problem, we will need to introduce trade-off. And we will introduce a trade-off parameter C. So this is what we will do. We will minimize 1/2 norm w square, which was a variant to the maximization of margin, and add this trade-off parameter C, which determines how much importance to give to the minimization of the error. C determines the trade-off between the error summation xi I and the margin 2 by norm w. Now let us see if we could develop a dual version, a dual problem to the support vector classification objective, such that we can deal with highly nonlinear separating surfaces. So the question we look at is, can we evolve a dual objective that gives us the kernel, which is a tool for nonlinear separation. You would also like to get an interpretation of the support vectors, and recall that for support vector regression we got that through the necessary and sufficient optimality conditions. We look at two approaches to showing the kernelized form for the dual. The second approach is derivation using first principles, and this is provided in the form of extra slide deck just for completeness. We will not be dealing with this in details, because this is very similar to the support vector regression setting. What we will however do is look at another approach, a very generic powerful approach that can be used to showing the kernelized form for the dual for several other classifiers and regression models. We have already seen logistic regression in its kernelized form, linear regression, bridge regression, and so on. We will now see that for support vector classification, and this theorem is called the representer theorem. So let calligraphic X be the space of examples such that the data set forms a subset of this space, and let us say there is a function k that goes from the space of examples to real numbers. It basically takes a pair of examples and outputs a real value. What the representer theorem says is that the solution f star in some Hilbert space of functions to the problem of minimizing the sum of errors evaluated on the function at each example plus a regularization component which penalizes complex points in this function Hilbert space can always be written in an alternative simplified form, which is summation over all the points of alpha I k evaluated on the query point and the data point xi. The only condition is that omega, the function that is applied on the norm induced in the Hilbert space, is a monotonically increasing function. This kernel k is called the reproducing kernel, and it is for the following reason. Now f is basically a function from the input space x to r, and so is k indexed by the specific example x, a function from x to r. Now if you take the inner product in the space of k evaluated at a point x with the function f, this turns out to be fx. This inner product is evaluated in the Hilbert space H. So what happens is that we are able to represent our evaluation functional by taking its inner product with an element of H. So this is called the reproducing property for the kernel K. So K is often also called the RKHS kernel or the reproducing kernel Hilbert space kernel. Let us look at what this means for the specific case of functions that are linear in some feature space phi. So let us say the function f was parameterized by w and b, or in general even just a single w where phi gets extended with a dummy entry 1. So if fx is w transpose phi x plus b and we are trying to minimize the complexity of fx by a norm on w, the parameter w here, and let us say like before we still had the error decomposing over the individual examples in the data set. So error is sum of the errors over the individual examples, where the function f is now w transpose phi xi plus b. Now k is assumed to be a specific form. K x prime comma x is phi x transpose phi x prime, the normal dot product in the phi space. Now it turns out that the solution w transpose phi x plus b can always be equivalently written as a summation over kernel evaluations of the input query x with every point in the data set xi scaled by some appropriate alpha I. As before, we would require the omega to be a monotonically increasing function of the 2 norm of w. Now the Hilbert space for us is actually Rn, and we are talking of the kernel k x prime comma x, which is phi transpose x times phi x prime, as the RKHS kernel. There is a significance to 2 norm here. So note that we would like the 2 norm to actually correspond to an inner product, and it turns out that only for the case of the 2 norm in Rn or Rn plus 1 do we have the inner product equal the square of the 2 norm. For any of the other norms we will not be able to define an inner product. Now what is the importance of this theorem for support vector regression? We already have a regularizer in the form of 1/2 2 norm of w squared, and 1/2 squared is indeed a monotonically increasing function. But what about the error function? Do we have an error function that linearly decomposes over the examples? Perhaps yes, but what to do with constraints? So let us revisit the support vector classification problem and see if we can cast the objective in this form. So recall the SVC objective: summation of error and the regularizer. The regularizer is also what gives you margin maximization. However, the error was characterized in terms of a whole bunch of inequalities. How do we do away with these inequalities? Can we merge them into the objective? So first of all, we will try and write these two inequalities as one. So the first inequality could also be rewritten as xi I greater than equal to 1 minus yi w transpose phi of xi plus b. The second one is of course xi I greater than equal to 0. Now xi I being greater than equal to two different quantities would mean that xi I should be greater than equal to the max of the two. So we could then write xi I as a quantity greater than equal to max of 1 minus yi w transpose phi xi plus b comma 0. What we next note is that xi I has no incentive to exceed the max of the two quantities on the right hand side, because we are interested in minimizing the sum of the xi i's. So the inequality in some sense is vacuous, and what we expect is that xi I should actually equal the max, and that is exactly what is being expressed here as a more compact constraint xi I equals the max of the two quantities. Now if xi I can be substituted into the objective, we can actually do away with the constraints, and that is what we have done here. What we have now is a summation of error terms, error decomposed across the examples, but this error is interesting. It is also called the hinge loss, and this is how the graph of the error looks like. In the positive quadrant, it keeps increasing linearly. However, for negative values of the error, xi I basically takes a max, which is 0. So here we have a summation over the examples of the error of the linear function fx at I with respect to the true label yi, and the second component is omega of the 2 norm of w. In this specific case, omega is half square of the function. So with this substitution, we will now be able to apply the representative theorem to support vector classification, so that phi x transpose w star plus b at the point of optimality must indeed be summation over the examples of alpha I k x comma xi. Now what should this kernel be like? Well, we have already said that this kernel k x comma xi is the dot product in the phi space of x with the phi of xi. Like in the case of support vector regression, we can deal with an implicit phi. And in fact, phi can be even infinite dimensional. What are kernels that correspond to such dot products? Well, we already seen Mercer kernels, so we could re-invoke all those concepts. So K could be any Mercer kernel, and we have also seen examples of such Mercer kernels, the Gaussian kernel, the polynomial kernel. In fact, if X happens to be text documents, you could also look at string kernels. If X has tree representation, you could look at tree kernels. X could be graph, in which case you could look at graph kernel, and so on. One could also go back to first principles and derive the dual optimization problem, which is completely kernelized, and that turns out to be very similar to the form for support vector regression. In the case of support vector regression, we had two parameters alpha and alpha star for each point I. What we have here instead is just one alpha I for each point, and pretty much all the constraints and equations are the same, but we have alpha I minus alpha I star replaced by just alpha I. Likewise for alpha j. Like in the case of support vector regression, the W vector optimality is a summation over the support vectors of alpha I times phi of xi, that is alpha i's with 0 values are not going to be support vectors. Most other interpretations follow through from the support vector regression case. I have provided additional reading for you about the support vector theorem, the RKHS and the proof of this theorem, as well as extra slides for your understanding of the derivation of the support vector dual using first principles. Thank you.